All right. Good afternoon. Just picking up where we're working with what we have with polynomial division, and we kind of cross into an additional theorem, and just looking at what we have from the exercises. Okay, we had in reference to page 280, and now we have in the case of working with polynomial division, okay, and there was the additional item that we had with the remainder theorem. And in fact, I'm going to show you both the synthetic division approach as well as the remainder theorem approach. And for what we have in the case of 35, okay, so you have x to the fifth plus 32 to be divided by the binomial expression x plus 2. And once again, just kind of going through the round of synthetic division. So just kind of setting things up, making sure that the coefficients are correct, and just setting things up in accordance with line division. Now, we're not going to perform line division, but I do at least want to get the setup to just sort of have things aligned, make sure that we have all the degrees in the polynomial from the fifth order all the way down to the constant, okay, to be represented. And for, again, so we have with the divisor, okay, so we have at x plus 2, and we have for the dividend, we have x to the fifth plus 32. Okay, so just looking at what we have in the dividend. So we have x to the fifth, and notice we have in the spread, we have missing fourth, third, second, and first order terms in x. So we're going to have quite an array of 0 placeholders. Okay, so we have 0 for x to the fourth. We have 0 for x cubed, 0 for x squared, and also we have 0x. And again, we have the dividend to close out with a constant. And so just translating this setup in terms of synthetic division. And again, I can use synthetic division since the divisor is first degree in x. And so looking at what we have in identifying the 0 of x plus 2. So if I set x plus 2 equal to 0, okay, we're going to have that x is equal to negative 2. And for what we have in the crossover to utilizing synthetic division, okay, so we have negative 2. Again, that's going to be separated from the coefficients of the dividend, and for the dividend, we have 1 for x to the fifth. And again, we have 4 zeros to follow, and this signifies the missing x terms from fourth degree on down to the first degree. And again, we have 32. And so in taking what we have here, okay, so we have the first coefficient in the dividend is also going to be the first coefficient in the quotient. So 1 is brought down. Then we have negative 2 times 1 is negative 2. 0 plus negative 2. Okay, so that is going to be at minus 2. Then we have negative 2 times negative 2 is positive 4. Then we have 0 plus 4 is 4. Negative 2 times 4 is negative 8. 0 plus negative 8 is minus 8. And then we have negative 2 times negative 8. Okay, so that would be 16. 0 plus 16 is 16. And negative 2 times 16 is negative 32. And 32 plus negative 32. Okay, so this is going to go to 0. So here we're going to have a remainder equal to 0. All right. Now, for the remainder theorem, I'm just going to mention, okay, so for the remainder theorem, Again, just restating. Okay, so if we had that f of x is divided by x minus c, then the remainder is going to be f of c Okay, so in reference to what we have in number 35, okay, so again, for your f of x, okay, we have f of x is equal to x to the fifth plus 32. And again, we had the divisor at x plus 2. And if I set x plus 2 equal to 0, again, I have x is equal to negative 2. And that c value and the corresponding x value from having set x plus 2 equal to 0. Okay, again, that is going to be at negative 2. So we have, in the case of the remainder, so you have the remainder, again, we have at f of c, and with c at negative 2. So we have f of negative 2, and applying negative 2 for the polynomial. Okay, so we're going to have negative 2 raised to the fifth, followed by the addition of 32. Negative 2 to the fifth is negative 32. We have plus 32, and that is equal to 0. And it turns out that, okay, for what we end up, okay, whether it's through the synthetic division or the line division or with the remainder theorem, okay, you're going to have the results will be exactly the same. Okay, so you have the remainder to be 0 whenever x to the fifth plus 32 is divided by x plus 2. So you could take long division, synthetic division, or since the divisor is a first degree, again, it's going to be at the 0 of the divisor that you can get the remainder upon taking the value of the function whenever the input is the 0 of the divisor. Okay, now for what we have in the case of number 36, and we have some similarity. Okay, we have again, we have the dividend, okay, to have missing degree terms, and here we have x to the fourth minus 81 to be divided by x plus 3. Again, if I were to go with the division route, okay, now if I set things up in accordance with line division, okay, so I have x plus 3 into x to the fourth minus 81. Okay, so you have missing terms in the third order, as well as the second order, and once again we have missing in the first order, and we have again closing out with a constant with minus 81. Okay, and again, just translating what I have in the setup along the lines of synthetic division. Okay, so if x plus 3 is equal to 0, and what's going to happen here is that we have x equal to negative 3. And again, so I'm just going to write this as well, since I'm going to be looking at both the synthetic division and the remainder theorem. So whenever we're talking about C, again, we're talking about the zero of the divisor. So x is equal to C is equal to -3. And so we have for the synthetic division, okay, so we have -3. And we have with the coefficients, okay, so you have 1 for x to the 4th. And we have 0 for x cubed, 0 for x squared, 0 for the missing x. Again, we have -81. Okay, so bring down 1. Then we have -3 times 1 is -3. 0 plus -3 is -3. Then we have -3 times -3 is +9. 0 plus 9 is 9. -3 times 9 is -27. 0 plus -27 is -27. Then we have -3 times -27 is a +81. And -81 plus 81 is 0. So again, so we have, once again, the remainder to be at 0. Okay. And if I take, again, just the remainder theorem approach, so again I have the dividend f of x to be at x to the 4th minus 81, and in the case of the remainder, again you have equal to f of c. Again, we had the c value from earlier at -3. And just substituting case, so you have -3 to the 4th minus 81. Now -3 to the 4th, so this will be 81. You have minus 81, and that is also equal to 0. Okay, so again you have the same result regardless of whichever approach you take. All right, now, and what we have for the next portion, okay, and we have just some items, and for number 41, okay, now we have a polynomial function, and this one, okay, we have with f of x is equal to 2x to the 4th, and we have minus 5x cubed, and we have plus x squared minus 7. Okay, and we have in the case of finding out, okay, what the remainder is going to be whenever the input is at 4. Okay, and let me just kind of mention this. The author doesn't explicitly mention this, okay, but you have 2x to the 4th minus 5x cubed plus x squared minus 7, and this will be over x minus 4. just mentioned. Okay, so we have with x minus 4 equal to 0, so we have x equal to 4. So we have x is equal to c is equal to 4. And if I were to take x minus 4 into this polynomial, okay, and find out what the remainder is going to be, so we have with x at 4, so we're looking at 2 times, again we have 4 to the 4th, minus 5 times 4 to the 3rd, and we have plus 4 to the 2nd, minus 7, okay, so we're going to have some big numbers in the mix. Okay, so 4 to the 4th, okay, that is at 256. We got minus 5. Now 4 cubed is going to be at 64. And we have 4 squared is 16. And so we have in the follow through, so you have 512 minus 320. And you have 16 minus 7, or you could just write this as plus 9. And just with the result here, okay, we're going to have the outcome to be at 201. Now, also in the case of determining the remainder, okay, by synthetic division, okay, so again, you have with your long division, okay, so you have x minus 4. Now, if you notice in the remainder theorem approach, I did not have to worry about applying any 0 placeholders. Now, if I go through long or synthetic division, especially with this dividend, okay, there is a missing term in the degree of first order. Okay, so you have 2x to the 4th, and we have minus 5x cubed. And we have plus x squared, so you have 4th order, 3rd order, 2nd order terms, but we're missing a first order term. Okay, so we're going to use 0x, and then we have followed by negative 7. Okay, and we have with the synthetic division again. The synthetic division, so just kind of looping together what we have had. So we have with the remainder theorem, also translating from long to synthetic division. Okay, so you have 4 isolated. Okay, so 4 represents x minus 4. Then we have for the coefficients of the dividend, so we have 2, negative 5. From x squared I have 1. You're going to have 0 for the missing first order x term. Then we have minus 7. And so we have with the synthetic division. Okay, so the leading coefficient in the dividend is 2. And it will also be the first coefficient in the quotient. Okay, so 2 is brought down. Now we have 4 times 2 is 8. Negative 5 plus 8 is 3. Then we have 4 times 3 is 12. 1 plus 12 is 13. And we have 4 times 13 is 52. 0 plus 52 is 52. And 4 times 52 is 208. And negative 7 plus 208. Okay, so that is going to be at 201. And once again, we have the remainder at 201. Okay, and again, those numbers are going to be the same. Okay, so we got the remainder from the remainder theorem in part A, and then we have through synthetic division in part B. And for what we have in the case of 42, okay, so we have with our function this time we're going from f of x to g of x. Okay, and now for g of x, now where you're looking for remainder, okay, so we have for the polynomial, so we have negative 3x to the fifth plus 2x to the fourth, and we have plus 6x squared. Okay, so if you notice we have the third order to be skipped, and we have minus x plus 4. Okay, and again, this is going to be divided. Okay, so this is going to be divided by x minus 2. So you have x minus 2 equal to 0. Okay, and so we're going to have the x's equal to 2. All right, so looking at what we have for the first part with the remainder theorem. Okay, so we have in the layout, okay, so we have the remainder at g of 2. So we have negative 3 times 2 to the fifth. And we have plus 2 times 2 to the fourth. Plus 6 times 2 squared. Okay, and we have minus 2 plus 4. Okay, and we have for 2 to the fifth. Okay, so that is going to be at 32. And we have plus 2 times 2 to the fourth. So 2 to the fourth is going to be 16. And for 6 times 2 squared, so this will be 6 times 4. And negative 2 plus 4, we're just going to say that's going to be plus 2. So we got negative 3 times 32 is negative 96. And plus 32 plus 24 plus 2. Okay, and so for what we're going to have in the mix, okay, so we got negative 96, so that negative amount is going to outweigh what we have in the total of the positive numbers, and so we have negative 96 plus 32, that will be negative 64. Negative 64 plus 24 is negative 40, and then in turn negative 40 plus 2, this will come out to negative 38. Okay, so we had the estimation of the remainder to be at negative 38 through the remainder theorem pathway. And for what we have in terms of, say, for the synthetic division, all right, so you have x minus 2 you have again taking into negative 3x to the fifth plus 2x to the fourth plus 6x squared. And notice once again I had bypassed a cubic term. Okay, so I have plus 0x cubed and we have minus x plus 4. And again, just for what we have in terms of synthetic division, so you got the 0 of x minus 2. Okay, so you have at 2 And for the coefficients, okay, so I have negative 3 and 2. Then we have 0 for the missing cubic term. Then we have 6 for x squared, negative 1 for minus x. Then we have plus 4. So we're going to have in the setup, okay, so negative 3 is going to be brought down. We have 2 times negative 3 is negative 6. 2 plus negative 6 is negative 4. 2 times negative 4 is negative 8. 0 plus negative 8 is minus 8. Then we have 2 times negative 8 is negative 16. 6 and negative 16 will make negative 10. 2 times negative 10 is going to be negative 20. Negative 1 plus negative 20 is a negative 21. 2 times negative 21 is a negative 42. And 4 plus negative 42, okay, so that will be at negative 38. So the last column total is at negative 38. And again, just like with the remainder theorem, okay, we have the remainder to end up at minus 38. All right. Now, for what we have with long division, okay, there's going to be a tie-in between the remainder theorem and what is going to be regarded as the factor theorem. Okay, now let me just tie these in together. So we have just to restate. Okay, so we have with the remainder theorem, again, if f of x is divided by the binomial x minus c, then the remainder is going to be f of c. And for what we have in terms of what is going to be the factor theorem, okay, this is going to be binary, like in yes or no. Okay, first of all, if from the remainder theorem, if the remainder f of c is equal to 0, then x minus c is a factor of f of x. And second, okay, if the remainder f of c does not equal to 0, then we're going to have that x minus c is not a factor of f of x. So where the factor theorem is going to come in, and we have with the next portion. So we have regarding number 48, now we have given a polynomial. Again, so we have g of x, and we have is equal to 2x to the fourth, and we have plus 13x cubed. Okay, we have minus 10x squared. You have minus 19x plus 14. And we have posed the question. Okay, so we have in part A. Okay, and this is asking is C equal to -2 a 0? In other words, it is asking is x plus 2 a factor of g of x? Okay, so if c equals -2 is a 0, then x plus 2 would be a factor of g of x. So again, we have with our polynomial, okay, so if I take the remainder, okay, so the remainder again, so we have g of c, and with c at -2, okay, so x is equal to c is equal to -2. So taking what I have with -2 and plugging in for x, so the input is at -2, and so we're going to have 2 times -2 to the 4th. Now we have plus 13 times -2 to the 3rd. And we have minus 10 times -2 squared. And we have minus 19 times -2 plus 14. Okay, so you have -2 to the 4th. Okay, so that is going to be at 16. Yeah, plus 13. Now, -2 cubed is going to be at -8. You've got minus 10. -2 squared is going to be at 4. Then we have -19 times -2, so this is going to be at 38. Yeah, plus 14. So we have so we have here, so we have 2 times 16 is 32. And we have 13 times -8, so this would be a -104. -10 times 4 would be a -40. And 38 and 14, that will make 52. So we have here, you got the positives to add up to 84. However, you got the negatives to amount to -144. And so we're going to have, with the remainder, this is going to be at -60. And since the remainder, g of c is equal to g of -2, turns out to be -60. And we have, going back to the factor theorem, okay, so you have your f of c, in this case g of c, is -60, which does not equal to 0. And so this is going to signify that we have -2 is not a 0. And you also have the x plus 2 is not a factor. Okay. Now, with the same polynomial, okay, so -2 is not a 0. Now, for what we have in the case part B, okay, so we have the question, okay, is c equal to -7 a 0? Okay. In other words, okay, is x plus 7 a factor? Okay, and so for the remainder on this one, okay, so with the same polynomial and testing out g of -7. Okay, so you have -7. Okay, so we have 2 times -7 to the 4th. You have plus 13 times -7 to the 3rd. We have minus 10 times the square of -7. We have minus 19 times -7. Plus 14. Okay, and I won't follow through quite as thoroughly as I did with g of -2, but here we got -7 to the 4th, and that's going to be a large number with 2401. And -7 to the 3rd, okay, so this will be minus 343. -7 squared, okay, so that's going to be 49. Now we have -19 times -7, so that is going to be positive 133. And we have plus 14. Okay, and once you take the products and then add and combine the constants, you're going to have ultimately that g of -7 is going to come out to 0. Okay, so for part B, okay, so we have for the remainder g of c is equal to g of -7. Okay, so this is equal to 0, and because we had the remainder to be equal to 7, okay, it is going to follow that -7 is a 0. And at the same token, we're going to have the x plus 7 is a factor of g of x. All right. Now, so we have with the various types of looking at determination of remainder, okay, through, say, line division, synthetic division, and also with the remainder theorem. Okay, we're going to, and also with the FOIL from the start of the course. Okay, we're going to sort of do a bit of an amalgamation of the techniques that surrounds everything involving multiplication and division, polynomials, and just tying together what we have been dealing with so far, and we're going to have for the next phase, and this will be determining determining factors of polynomials from given zeros. Okay, all right, so now we looked at given zeros like in the case of forming factored and expanded forms of polynomials. But now, let's say that, okay, where we're looking at given zeros, and now you're looking at determining factors of polynomials. Now let's say that, just to kind of get into, let's say, like for factors of a particular polynomial. Now let's say that if we're looking at determining factors of, let's say we have a polynomial f of x is equal to 2x squared minus 6x plus 4 given that we have that 2 is a 0. Okay, so you have that 2 is a 0. Okay, and what you're going to do, okay, so you got this polynomial 2x squared minus 6x plus 4, and we have that 2 is a 0. And we can sort of set things up along the lines of synthetic division. Okay, so if I take synthetic division, okay, and so with synthetic division, now we have 2 is a 0. And if I take the coefficients of the dividend, okay, so I'm not going to go through the long division setup. We've got a second order term, a first order term, and a constant. So there are no missing degree terms. So you got 2, negative 6, and 4. And let me mention, okay, so if 2 is a 0, then the remainder should also be 0. Now looking at what we have here, so the leading coefficients in the dividend is going to be at 2. This is going to be brought down. So 2 is brought down, then we have 2, the 0, times 2 is equal to 4. Then we have negative 6 plus 4, which is going to be negative 2. And then we have 2 times negative 2 is going to be at negative 4. Then we have 4 plus negative 4 comes out to 0. So the remainder is equal to 0. And for what we have in terms of the quotient, okay, again, for the 2 at the top, this is in reference to 2x squared. And for the 2 brought down, this will be in reference to just 2 times x of first order, and then we have minus 2. And with 2 as a 0, okay, now you're going to have that the divisor is going to be at x minus 2. And for the factors, we're going to have, in this case, right, so we're going to have 2x squared minus 6x plus 4. Again, that's going to be equal to the product of the quotient, which you have at 2x minus 2. We have times the divisor, which is going to be at x minus 2. And then we have just for the complete factorization. Okay, so we have with 2x minus 2, greatest common factor is going to be at 2. 2 will go into 2x minus 2, x minus 1 times. And then we have times the quantity of x minus 2. Okay. Okay, and so that will be the outcome we have here. And let's say that as another scenario, say we have factoring. Let's see here, f of x is equal to 4x cubed minus 20x squared plus 33x minus 18 given, okay, we'll say also that 2 is a 0. Okay, So you're going to have, again, utilizing synthetic division. Okay, so again, we have 2 is a 0. Again, making sure we're not missing any degree terms in the polynomial. So you got third order term, second order term, first order term, and a constant. So we'll go ahead and write out the coefficients. So no 0 placeholders are necessary. So we have 4, negative 20, 33, and negative 18. And again, if 2 is a 0, then the remainder should be 0. So we have here, if we bring down the leading coefficient 4, so you got, with 4 brought down, we got 2 times 4 is 8. And we have negative 20 plus 8. Okay, so that is going to be at negative 12. 2 times negative 12 is going to be at negative 24. And 24, or 33 plus negative 24. Okay, so that is going to be at 9. Then we have 2 times 9 is 18. Negative 18 plus 18 is 0. Again, if the assigned value is a 0, then the remainder should be 0, which it is. And we have, in the case of the quotient, okay, so the 4 at the front was in reference to x cubed, but with it brought down, this will be in reference to x squared. So you have 4x squared minus 12x plus 9. And again, with 2 as a 0 presented once again, we have with the divisor. Again, this is going to be at x minus 2. Okay. So for the factorization of what we have with this polynomial, okay, so you have the divisor times the quotient, or the quotient times the divisor. So you have 4x squared minus 12x plus 9. And we have times the divisor, x minus 2. Now it might be that with the quotient times the divisor, you might have the simplified form already. But with the quotient, now this one can be factored. So with 4x squared, now this will go to 2x and 2x. And with 9, okay. Again, you could do stuff like factoring by grouping. And you're going to have a repeating binomial expression with 2x minus 3. So the condensed form in this case is that we're going to have 2x minus 3 quantity raised to the second power. And we have times x minus 2. And that will be the result for this one. Okay. And okay, now let's say that if we have, just as a exercise right quickly, okay. And we're going to need a 0 placeholder, so just want to go ahead and tell you in advance. Okay, let's say that if we have, and this is one where we're going to have the quotient and the divisor will be the factor, so no further expansion. But let's say if we have factoring f of x is equal to 3x cubed minus 41x minus 28 We'll say given that 4 is a 0. Okay. So for the next few moments, let's see what we get in factoring 3x cubed minus 41x minus 28 on the basis that 4 is a 0. Okay, just for what we have here. Now, if you go ahead and work with the synthetic division, okay, just make sure there's no missing degree terms. So we have with the dividend, okay, so you have f of x, and if you notice we have 3x cubed, okay, and the next term is first order, so we have a missing second order term. So we have like f of x will be 3x cubed plus 0x squared minus 41x minus 28, and again we have that 4 is a 0. So if we go through the pathway, okay, of synthetic division, again, so we have 4 is a 0. And for the coefficients of the dividend, so you have 3 for 3x cubed. And then we have 0 since we have a missing x squared term. Then we've got negative 41 for the first order x term. And again, we have the constant negative 28. So looking at what we have in applying synthetic division. Okay, so 3 is the leading coefficient. This will be brought down. Okay, so then we have 3 multiplied by 4. 4 times 3 is 12. And we have 0 plus 12 is 12. And then we have 4 times 12. Okay, so that is going to be, in this case, at 48. Negative 41 plus 48, okay, is going to be 7. Then we have 4 times 7 is going to be at 28. And negative 28 plus 28 is 0. So the remainder is going to be at 0, which we want, okay. Otherwise, if it were not, 4 would not be a 0. So the remainder is equal to 0, and as for what we have in the case of the quotient, okay, so this 3 at the front, okay, this is going to register as where the first term is going to be 3x squared, and we have plus 12x plus 7, and we have in the case of the divisor, so 4 is a 0, so think of it like if you have x equal to 4, and you set this up as an equation equal to 0, well, that which would be equal to 0 would be the divisor, which in this case is going to be at x minus 4. And so for the factoring, okay, so we have 3x cubed minus 41x minus 28, and this is going to be equal to 3x squared plus 12x plus 7 from the quotient, and then we have times the divisor, which will be at x minus 4. And in terms of integers, okay, this is already going to be in simplest form. For there are no factors of, say, 3 times 7 is 21, and there are no factors of 21 that will add up to 12. You can think of 3 as 7, 21 and 1, and your sums will be like at 22 and 10, but there's no integer combination that will add up to 12. Okay, so this is going to be completely factored. With the real integer coefficient. So again, 3x cubed minus 41x minus 28 is equal to, again, the product of 3x squared plus 12x plus 7 times the quantity of x minus 4. Okay, now also tying in some of the earlier topics, especially with domains of functions. And now for the next section, and we're still in a sense dealing with polynomial division, and this will be in the case of what we have in the crossover to asymptotes, namely vertical asymptotes. And for this portion, so what we have with domain and vertical asymptotes. Okay, and again, just for a rational function, it could be f of x, but I'm just going to label this as r of x. Okay. Okay, we have for a rational function r of x. Now we're going to have for the domain. Now I said this before for f of x. Now we have for the domain. Okay, this is going to be the set of all values x such that the function is defined. In other words, defined as being a real number. Now where we have vertical asymptotes. Okay, now for a vertical asymptote, okay, that is going to be a vertical boundary line. It's going to be a vertical boundary that separates the graph of r of x into separate sections. Okay, so you have like r of x, the graph, instead of running continuously, we have like split up into different regions. And now the vertical boundary, okay, so it's going to separate, and the vertical boundary is going to be formed by exclusions from the domain. Okay, so you have exclusions from the domain. So you have like those restricted values. Okay, and you have those exclusions from the domain whose factors remain. Now place emphasis on this. Okay, so it's going to be whose factors remain after R of x is reduced to lowest terms. Okay. All right, and just kind of give you a kind of an opening in terms of domains and vertical asymptotes. And we'll say we have, for instance, say if you're looking at determining the domain and vertical asymptotes, if any. And we'll say that we have as a first rational function. I'll give you one that is already in reduced form. And we'll say we have R of x is equal to x plus 1 all over x plus 4. Okay, so we're looking for the domain. Okay, now for a rational function to be defined, okay, now the denominator cannot be 0 in value. Okay, so x plus 4. Now x plus 1 can be 0, so you can have a 0 numerator, again, as long as you do not have a 0 denominator. So we have x plus 4 cannot be 0, so we have the x cannot be negative 4. So we have for the domain, you'll have everything that will be less than negative 4. So you have the interval notation for this, and you have combined with those values of x that will be greater than negative 4. And again, the interval notation, you have parentheses with negative 4 and positive infinity inside. Okay, and again, since x plus 1 over x plus 4, since this is already in simplest form, that means that with negative 4, since this stems from x plus 4, which is not going to cancel out, x plus 4 remains. So it's going to turn out that with the vertical asymptote, this will be the exclusion from the domain. So in other words, that which was restricted, but whose factor still exists in the simplified version of the rational function, okay, that is going to be the vertical asymptote, and that's going to be written as x is equal to negative 4. So just giving a little bit of visual on this one. Okay, so you have a rational function. So again, working with the xy coordinate system. Now I'm just mentioning, okay, so we have an x equal to negative 4. Now I'm just going to do kind of a sketch on this one. So again, this is going to be a vertical boundary. That's going to split the graph of R of x. Again, this is going to be just a little bit of a rough sketch, but for r of x equal to x plus 1 over x plus 4, for the graphing sections, we have split into two different regions. Again, I'm not drawing this according to scale by any stretch of the means, but just for the nature of r of x equal to x plus 1 over x plus 4, okay, you're going to have those areas split up into sections. And let me add in also, okay, now the graph of r of x never touches a vertical asymptote. It might come close, like running tangent, but it will never come into, strictly speaking, it will never come into contact. Okay, so this function r of x, okay, that is already in simplest form. Now, and let's say that if we have a case here, and we'll say that where the simplest form is going to be stressed, and we'll say we have, for instance, okay, if we have the r of x is equal to x squared minus 1 all over x squared plus 3x plus 2 Okay, so we have r of x equal to x squared minus 1 over x squared plus 3x plus 2. Okay, just a minute.
Due to inclement weather, JPC is closing today at 2 o'clock p.m. All asynchronous and synchronous classes will continue to meet virtually as scheduled. Employees should transition to a remote working location at 2 o'clock. Please remember to shut down all of your IT electronics and ensure all windows in your area are closed securely before leaving campus. Normal operations will resume tomorrow. Repeat, due to inclement weather, JPC.
Okay, anybody who has face-to-face classes at 2 o'clock on campus, those classes have been canceled. So the college, not the synchronous classes or the asynchronous classes, but the college, anybody who meets face-to-face will not be doing so for the rest of the afternoon and evening. All right, so we have with r of x equal to x squared minus 1 over x squared plus 3x plus 2. Again, you're going to look for the exclusions from the domain before doing any kind of reduction. So for the domain, okay, again, we want to keep r of x defined. So you have x squared plus 3x plus 2 cannot be equal to 0. And looking at factoring, okay, so you have x plus 2 times x plus 1 cannot be 0. So if the whole expression cannot be 0, neither can its factors. Okay, so you have x plus 2 cannot be equal to 0. So we have the x cannot be equal to negative 2. And for x plus 1, if that cannot be equal to 0, okay, well, we have the x cannot be equal to negative 1. So we're going to have a couple of exclusions from the domain. Okay, so when we have those values at the lowest end, we have those values leaving out -2. And still leaving out -2, we have those values of x between -2 but not including -2, but not including -1. So -1 is also left out. And for what we have for the rest of the domain, we have those values of x that will be greater than -1. Right, so that's going to be the domain. Now where the asymptotes, vertical asymptotes might appear, so just taking what we have now, so just representing, okay, the rational functions. You have x squared minus 1, and if I factor, we have the quantity of x plus 1 times that of x minus 1. And for the factorization of x squared plus 3x plus 2, so I have the quantity of x plus 2 times that of x plus 1. And guess what? We have a common factor between the x plus 1s. Okay, so we have in the setup. Let's go write this again. Okay, so we're going to have x plus 1s are going to cancel. And the completely reduced form of this rational function, okay, we have x minus 1 all over x plus 2. Okay, and if you notice, okay, we have with x plus 1 cancels, or with it canceling, and since x plus 1 cancels out any exclusion from the domain whose factor cancels out, this signifies that instead of being an asymptote, it's going to be a hole in the graph. And for what we have in the case of the denominator, okay, we have x plus 2 remains after the reduction. Okay. So this means that since x plus 2 remains, we're going to have what could have been 2 vertical asymptotes, but instead will be only 1 vertical asymptote. So you have the vertical asymptote is going to be at x is equal to -2. So you got your domain and you got the vertical asymptote. And just putting what we have all together, and we're just about there. Here we go. Okay, so you're going to have a vertical asymptote at x equal to -2. And for what we're going to have in the case of the graph itself, okay, so this one is going to be split once again. So you have x equal to -2, and we have the graph again to be split into separate sections. I'm just going to mention as well the other portion. Okay, so you have this part as we get closer to -1. and instead of an asymptote, okay, you're going to have a hole at x equal to -1. So any factors that remain for the exclusions from the domain, those exclusions will be vertical asymptotes. But if they cancel, that means that we're going to have, instead of a vertical asymptote, we're going to have a hole.